Right, hello again. This is feedback for section B, the extended questions on the organic mock that you did last week in April. Okay, so question about unsaturated hydrocarbons. Why does A have a lower melting point than compound B? Very important that you mention that your 2 marks came from the fact that it's branched and has less surface contact, A. Therefore, there are weaker London forces and less energy is required to break them. You needed that information for your 2 marks, and so some of you didn't get the 2 marks, just got 1 mark for recognising the branching and the surface contact. Remember this surface contact thing, okay, which some of you have, and it's not surface area, it's surface contact. Okay, cis-trans, name compound C, hex 3 ene1-ol. I think some of you put 1-hydroxy hex 3 enol or something, which was acceptable. Okay. Definition of stereoisomer, you should know this. You know, it's got the same structural formula. That's the important thing. The same structural, obviously the same molecular formula, but the same structural formula, but a different arrangement in space. That's what makes it geometric isomer. And then you've asked to draw the structures of cis-trans isomers of compound C, which you were given. It's easier, I think, if you write it in this kind of bow tie arrangement where you're branching them off like that, but you know, it's up to you how you do it. I just think it's easier to see when you're actually drawing it which isomer you've got. Some of you did get confused, so you need to know the difference between cis and trans. So don't forget cis for sisters on the same side, or however you want to remember it. Yeah, this diagram asking you about how a pi bond is formed, showing how p orbitals are involved in the formation of a pi bond. You just needed to draw the 2 p orbitals here, and then the representation of the pi bond. I mean, you didn't even have to label it according to the mark scheme, but you did need the 2 lobed p orbitals, and you needed to show that they'd overlapped sideways effectively, and they were above and below the plane. It's only 1 mark, so you need a lot of detail. Okay, so you're told that this reacts by electrophilic addition, and you get 2 different products formed. So straight away you should think Markovnikov's rule. Okay, so suggest how hydrogen bromide molecule can act as an electrophile. So this, you needed to refer basically to the definition of an electrophile and show how it applied to hydrogen bromide. So it refers, obviously an electrophile is a substance that accepts a pair of electrons. So if you'd said the hydrogen accepts a pair of electrons, that was fine. You didn't need to go into detail about it approaching the electrons and stuff, because it is a polar molecule. And then you're asked to draw the 2 possible organic products for E and F. So you've got this one where the bromine is attached to this carbon, and this where the bromine is attached to this carbon. And here is the mechanism that you are asked to draw, which would give you, it just says to show either E or F, it doesn't matter which, because you've decided which one is E and which one is F here, you're not specifically asked. So yeah, you need to get all those curly arrows in, you need to put the dipoles in, and you must make sure that this is a full positive charge here. Once the electrons have formed a bond with the hydrogen, this carbon is now electron deficient, and that obviously makes room there for the bromide ion to come in and attach itself to the carbon. Again, lone pair. So those curly arrows, very important where you place them. I cannot stress this enough. You lose stupid marks if you've done the correct mechanism, but your curly arrows are not exactly precisely placed. Okay, so here's the product. And then you're asked which one would be major, and then to explain why. So in my case, the major product would be E, because it's attached to the carbon. So this cation would have been a tertiary cation. This carbon is attached to 3 carbons, 1, 2, 3. whereas this carbon is only attached to 2 carbons and 1 hydrogen. And that's the explanation I've given. Okay, and that's what they wanted. They didn't want Markovnikov's rule. The reason I said think about Markovnikov's rule is to tell you where the hydrogen would attach itself, and then you have to think about why that is. Okay. Part E is a long old question. So we're given a hydrocarbon here with 3 double bonds, and then you are asked to do a calculation related to 204 milligrams. So the first thing you need to do is convert your milligrams to grams, because you can't work anything out with milligrams. And you're asked to calculate the volume of hydrogen gas at room temperature and pressure. So you don't need the ideal gas equation for this. This is the straightforward equation, you know, volume over 24 or 24,000. Here we're asked in cubic centimetres, so it will be 24,000. So work out your moles of myrcene, yeah? You know that you need 6 hydrogen atoms because you've got 1, 2, 3 double bonds, so 2 hydrogen atoms for each double bond to react with that, which is basically 3 moles of H2, isn't it? So your ratio is 1 to 3. So you need 3 times as many moles of hydrogen as you had myrcene. So you just multiply it up by 3. So that tells you the moles of H2. And then you can convert that to a volume by multiplying by 24,000. So this is not a difficult calculation at all, unless you can't, first of all, unless you don't know how to convert milligrams to grams, which I think some of you got stuck with. And secondly, remembering all the different mole equations, which one is relevant here. Room temperature and pressure, you don't need to use the ideal gas equation. Okay. Right, beta carotene is a naturally occurring unsaturated hydrocarbon. Okay, it's got 40 carbons, 2 rings, and a branch chain. And you're told that you've got 0.02 moles of beta carotene, and it reacts with 5.28 cubic decimeters of hydrogen gas to form a saturated hydrocarbon. Using molecular formulae, construct a balanced equation for this reaction. So that's what you're aiming for here. So you need to, and as it says, you need to show some calculations and some reasoning. So I've just scribbled down there the equation that I'm going to need. So I can work out my moles of hydrogen because we've got a volume. Yeah, so we've got moles of that. We can work out our number of double bonds because we know how many moles of beta carotene we've got, and we now know how many moles of hydrogen, so we divide one into the other, and that tells us there are 11 double bonds. Now, even if you'd only done those 2 parts of the calculation, you would have got a couple of marks. Okay, so the molecular formula, I've worked this out by, we're told it's got 40 carbons, right? If it's got 2 rings, then it must have 2 hydrogens less, effectively. It says a branch chain, but that doesn't indicate there's any double bond there or anything. So where it would be, if this was just a straightforward alkane, the molecular formula would be C40H82, using the 2n plus 2 rule. But because we've got 2 rings, we have lost 4 hydrogens, because you lose 2 per ring. So 78 minus 22 is 56. So that means your starting beta carotene must have a molecular formula of C40H56, and you're adding in 11 moles of hydrogen, and that gives us C40H78, and that's your equation. That's what you're asked for. So you need to show these 2 little bit more complex pieces of information to get the second 2 marks, and that's obviously what differentiates between, enables the exam board to differentiate between the higher level student and the student who can just calculate moles. Okay. Right. Okay. So now we're looking at benzene, thinking about the reaction. So obviously we've moved on to second year stuff now because we didn't do this in the AS year. So you're asked to outline a mechanism for the nitration of benzoic acid and show how sulfuric acid behaves as a catalyst. So you've got to put all that information in to be able to get all the marks for this question. So first of all, you need to form the electrophile using your conc acid, conc sulfuric, conc nitric, and we end up with NO2+. We need the NO2+, remember, because benzene, the electron density is so spread out, it will not create a dipole in an approaching molecule. Okay, so we've got NO2+, and the rest of the equation. And the mechanism, pretty straightforward, as long as you realise that obviously curly arrows go from electrons to electrophiles, and some of you still drawing from positive charge towards negative, which never ever happens, so you can't get that mark ever. So the electrons in the ring are attracted to NO2. Now if you show that your NO2 is attached here and you put your hydrogen in, you must show this horseshoe with the positive charge in the middle pointing towards this carbon. If you don't, you lose a mark. Okay, and some of you didn't do that, so you obviously lost your mark. So this is the intermediate, so we've still got a hydrogen here and an NO2, so the curly arrow goes from the bond in the hydrogen towards the center of the molecule, and don't forget at the end here that you have to put H+, because the hydrogen is now lost. Your NO2 is attached, but your hydrogen ion is lost. And then finally you need to show how the catalyst is regenerated, so that hydrogen ion joins with the HSO4 minus ion and reforms H2SO4. In that case you would get all 5 marks. And that really is not a difficult question if you've learnt electrophilic substitution reaction for benzene. Yeah, 5 marks, that's a lot of marks for a relatively easy answer, I think. When you compare it to some of the 6-mark questions that you have to answer and the information you have to put in there. And here is one. So we've got our star up here, or our asterisk, which is telling us that they want to see a detailed answer. Describe a method to obtain a pure sample of your 3-nitrobenzoic from the impure solid. So you're told that you've got your impure solid, so you're not actually making the nitrobenzoic, you're just literally purifying. You're asked to determine the percentage yield using the information you're given here, and how would you check its purity. So just do this in a methodical way. Part 1 is to describe a method. Now you're going to recrystallize your impure solid, and you've done that, so you should know the procedure. And I've written it out here. We take our impure solid. Crucial word here is to use is the minimum amount of hot solvent. So you dissolve it in the minimum amount of hot solvent. They're not asking you for a method. They're not saying how do you do that. So you get a water bath and you put this in here and put that in there. They're not asking for that. And some of you did go into that kind of detail, which won't get you any marks. They are just asking you for a method to purify. Okay, cool and allow crystals to form. This will be your pure 3-nitrobenzoic acid. Your impurities will be left in the solution. Filter under reduced pressure, wash with cold solvent and dry. That's how you would recrystallize your substance. Second part, percentage yield. Work out your moles of benzoic acid from your mass up here. Okay. Work out the moles of nitrobenzoic acid, again from the moles in question. Yeah, obviously you need to work out the molar mass of these two, so you need to know what they look like. And then it's a 1-to-1 ratio, so basically divide the benzoic acid moles into the nitrobenzoic acid and multiply by 100. Okay, so there's your 71.3%. And then the final bit is to check purity. So there are a couple of ways you could do that. So some of you talked about a melting point. So if you take a melting point, crucial thing is you have to state that you would then compare the value to a data book or a published value. If your sample is pure, it will have a sharp melting point. Okay, or you could have said TLC, compare your RF value to published data. Could also have said take a spectrum, an NMR or an IR, but I wouldn't worry about that. Okay, so those, you know, you've got two options there, how you would check purity. And if you write it out like that, you would definitely get 6 marks, providing you obviously had all the steps in and things. Okay, so we're looking at these 3 molecules here and looking at the relative ease of nitration, and you're given some conditions. It asks for the trend, and I don't know what some of you wrote loads of stuff here. It's 1 mark only, yeah? So the trend is that as you go from phenol to benzoic acid, it gets harder to nitrate. It's not asking you why, it's just asking you to state the trend, literally. Okay, so I've tried to explain here. Phenol is the most reactive, benzoic acid is the least reactive. You don't need to say that, you just say the trend is that they get less reactive moving from phenol to benzoic acid. And then you're asked to explain why that is the case. All right, apply your knowledge of the bonding in arenes to explain the trend in this part of the question. So you need to know, obviously, that with phenol, that the lone pair from the oxygen on one of them is partially delocalized into the pi system, which gives a higher electron density and makes it more reactive. With benzoic acid, of course, you've got that COOH group, which is actually electron withdrawing. So the electron density is lower in benzoic acid, so it's less likely, it's not going to be as reactive. Okay, and that's an application. Again, this is differentiating, yeah, in terms of how much you understand the chemistry. Okay, now we've got one of these schemes of like synthesis map. Okay, so we're looking at synthesis of 3-bromophenylamine. Yeah, this one here, sorry, here, bromophenylamine, starting from nitrobenzene. Complete the flow chart. So this is where you need to have your synthesis map in your head, ready to, you know, as I said to you, all of you, you really do need to learn them off by heart. And if you can scribble them down as soon as you get into the exam, then you can very quickly answer a question like this. Yeah. So you've got your nitrobenzene here. If you're going to bromination, obviously the reagents are Br2 plus the halogen carrier. Yeah, because Br2 will not be polarized by benzene. The electron density is not high enough, so you need the halogen carrier. So your bromine will then attach here. This is your intermediate. If you want to reduce that now to get our NH2 group, it's tin and conc HCl. Okay, and then again a little bit of application again. So 3 marks for just knowing the scheme, which you can know or learn off by heart. This one you have to think a bit more about. If you did the reduction first, you would have NH2 on your ring, which is a different directing group to NO2. Okay, and they would be your 2 products. Okay, this one pretty straightforward, I think. Sodium cyanide, which is obviously where we add in a carbon to our carbon chain. 1-chloropropane. You know, just draw it out, but make sure that the bond that you are where the bond is breaking and reforming, that you've actually drawn out the bond there. Always put in the charges, the partial charges, and then obviously your curly arrows got to go. Don't forget on cyanide ion, the lone pair is on the carbon, not on the nitrogen. All right, so that comes in, that bond breaks, and then don't forget your Cl minus, because I think some of you did, and you lost a mark for that if you didn't have the Cl minus. Pretty straightforward though if you know that mechanism. So another synthesis here, And again, if you've got that synthesis map in your head, or you manage to scribble it down, it will help you do this much quicker. Yeah. So you're given a partially completed flowchart. Yeah. And well, you have to establish what compound G is from some of the products. Yeah. Okay. So you've got a carboxylic acid with an alcohol group on here. This is a nitrile, and this is an amine. So you know, how are we going to get to these different things? So we need an aldehyde to start with to form our, if you look at the reagents here, sodium cyanide and H+ acid. Okay, so that will be an aldehyde, forms a hydroxynitrile. Reaction 2, then to convert that to an amine, we need to reduce it. Yeah, so hydrogen and nickel. And this one, we will need to hydrolyze it. So aqueous acid, aqueous, H2O, HCl, or HCl with aqueous in brackets, but you need to indicate that water has to be present for hydrolysis. Okay, so again, if you've got your synthesis map in your head, that would not be difficult. Okay, lone pair, compound H reacts with dilute hydrochloric acid to form a salt. Explain why compound H can react with dilute hydrochloric acid and suggest a structure. Okay, so compound H, here we are. Okay, and obviously as the lone pair on the nitrogen, means it can accept a proton, draw out the structure. Don't forget the positive charge, it's accepted a proton, and the Cl minus. Okay, polymers, which seem to cause a bit of confusion for some of you. The thing I would say, and I've written it out here to say that the way they've drawn compound I up here, I think it's deliberately drawn like that to kind of make it a little bit harder to see exactly how this polymer would form, because you can put that OH on the end here, yeah, and it becomes more obvious then that you've got the acid joining with the alcohol. So that's what I did when I drew it out. Put my OH on the end, my carboxylic acid on the end, and then you can see that one end joins to the other. Don't forget, you lose the OH from this end and the H from this end to form your ester. So your O has to have a trailing bond, and on this side the OH it doesn't exist, so your C double bond O has a trailing bond. Okay, you were asked for 2 repeats, so you only had to draw 2 repeats. And then the last question is recognizing that because you can hydrolyze esters, they will obviously biodegrade. Polymer again, draw the structures of the 2 monomers that can be used. So you need to recognize you've got your amide link here. So you split that and just basically add back the OH group to your carboxylic acid and the hydrogen to the amine, because you know that's how you form your water and that's how they come together. So that's very straightforward. As long as you've got enough carbons and things, make sure that you just double check your structure. Okay, this one flummoxed a few people, but you're told that you've got a sample that has a relative molecular mass of 21,500, and they are asked to estimate the number of repeat units. So you need to go to your repeat unit and work out the molar mass of it just by adding up your carbons, your oxygens, your hydrogens. Double check it, make sure you've got all of them. So the molar mass of the repeat of the sample, sorry, of a repeat unit is 226. You've got a sample with 21,500, so you just divide one into the other. Okay, alcohols. An equation for the complete combustion of an unsaturated alcohol. So obviously it's unsaturated, you're only going to have 10 hydrogens. Okay, and then it's straightforward. This one, I was surprised how many of you didn't achieve all the marks for this. I mean, it's only 2 marks, but you should be able to draw a hydrogen bond and, you know, recognize how you draw a hydrogen bond. This is obviously from last year, but it, you know, they come up all the time, hydrogen bonds. So your lone pair, you must show the lone pairs on the oxygen, and your hydrogen bond must go from a lone pair to a hydrogen. Some of you did 2 ethanol molecules, which you're not asked for. You're asked for ethanol and water, and you must show the dipoles. Okay, so your lone pairs, the dipoles, your hydrogen bond, that's it. All right, make sure you've got all of those on there. You're actually asked, you're told in the question, include relevant dipoles and lone pairs, so you even have to remember to do it. But it's very important that you can't just put 1 lone pair on here, put the 2 and show the hydrogen bond. And then this question, yeah, this one has obviously got 2 OH groups, and this has only got 1 OH group, so it's going to make more hydrogen bonds, therefore it will be more soluble in water. Crucial thing is that you have to make a sort of comparative statement. You know, that hexane 1,6-diol has got twice as many OH groups as hexane 1-ol. That's why it's more soluble. Okay, yet another synthesis. You see how important it is that you are, you know, you really know these syntheses. Yeah. So you're given this compound K in the middle here, and basically asked to fill in the rest of the flow chart. So if you reduce something, we've got something up here that you're reducing to form an alcohol. Yeah? So if you're reducing, if you're forming an alcohol, it's going to have to be a C double bond O, yeah, and the reagent is NaBH4. This one you're just substituting the alcohol group basically for a bromine. Remember these conditions are from AS, where you have to produce the halide ion is formed in situ in the reaction mixture. So sodium bromide, you can't just add in hydrogen bromide or something like that. Yeah, it's actually produced in situ. And then if you add an acid catalyst and heat it, we get a dehydration. So the water will leave and will form a double bond, and these are the 2 possible structural isomers. Okay, so this is a dehydration, this is a substitution, and this is a reduction. The name of compound K, which is here, okay, some of you put this as phenol, but it's not, obviously it's a cyclo compound, it's not benzene. So 3-methyl-cyclohexanol. Okay, this one, again, this is AS stuff, so it shows you the relevance of making sure that you are looking at your AS folder, notes and things, as well as your A2 stuff. You know, because this is 5 marks and it's really easy, yeah, as long as you just do everything that they ask you to do. So basically you're told that butan 1-ol can be oxidized to form 2 different products, and depending on the reaction conditions used, describe both of them and include this information. So just make sure you've included it. So the structure of the organic product, a balanced equation, and the essential reaction conditions. You do it for both. Okay, and then the last couple of questions are a little bit more complex. They are all A2 content. So, well, actually they're not, because it's mass spectrum and infrared is AS, but the way that it's kind of put together with NMR is obviously more of an A2 question. Yeah. So you're given a mass spec, you're asked to work out the molecular formula of this compound. So you can work out the empirical formula first by using the percentages, and then the molar mass of this empirical formula is 68. Now your molar mass of your substance is 136, which you take from your mass spectrum. Yeah. Don't forget that you don't look at the very last one. That is related to carbon 13. So there are two lots of, if you divide 68 into 136, it goes into it twice. So that means you must multiply your empirical formula by 2. So we've got that C88802. Then you are told that qualitative tests are carried out on an aromatic compound, and you're told that its pH is 5, which is slightly acidic, and you get an orange precipitate with 2,4-DNP, but you don't get an observable change with toluenes, and you don't get an observable change with sodium carbonate. So if this was a carboxylic acid, obviously you would get you would see fizzing, and if it was an aldehyde, you would get a silver mirror. So this is actually a ketone and phenol. All right, they're the two functional groups that you recognise here, and I would suggest that most of you need to read up on phenol, because I don't think anybody got that right. You got the ketone bit, some of you, but you certainly didn't get phenol. And again, the reasoning is there. Can't be a carboxylic acid because there was no carbon dioxide produced, but it is slightly acidic. Okay, then you're given the carbon 13 NMR spectrum and asked to use the spectrum and your results from A and B to determine the structure of the compound, with an explanation for your reasoning. So here we've got 1, 2, 3, 4, 5, 6 different environments for our carbons. Yeah. So we know there's a phenol, we know there's a ketone, we know there's a benzene ring because there are 4 peaks between 115 and 160 parts per million. Be specific here, else you don't get the marks. There is a C double bond O peak at 190, yeah, and CC peak at 24. All right. But then it's just a matter of trying to put it together. 6 different carbon environments, but because you didn't, I don't think anyone got the phenol, so I don't think anyone got the structure of this compound right. Okay. The crucial thing is use all the information given to you, and don't forget to quote values from the spectrum. And then finally, this has got your star here, so they're expecting a fluent, coherent answer, giving all the information in a kind of ordered way. So you're given a proton NMR spectrum, and you're given 2 infrared spectra. Yeah. Now, please, use this sequence to go through when you're looking at NMR. All right. So, what do you know about the substance? That's the context. How many environments? What is the shift? How many hydrogens are there, the area or the integration? And then finally the splitting pattern, which enables you to put them into order. So I've written it out in a very sort of ordered way. I've literally gone using these headings. So the context is that we know it's made of carbon, hydrogen and oxygen. When it's refluxed with aqueous hydrochloric acid, it forms 2 compounds, M and N, for which we have the infrared spectra. So you need to refer to those infrared spectra and be specific about the peaks. So we can see from the spectrum that M that it is a carboxylic acid because of these 2 peaks, OH and C double bond O. And this is a broad, very broad peak. N has a broad peak around about the same wave number, but it's not as broad, so it indicates an OH group from an alcohol. So there we are. So we know we've got a carboxylic acid and an alcohol that can be formed from L. So that tells us that L is an ester. So we know what we're looking for. So then we've got to analyse the NMR spectrum. So now we move on to the environments. There are 4 of them. look at the shifts and just scribble down what they indicate from your data sheet. Yeah, so this one is, you know, CH, this is CH, this one is CH attached to C double bond O, and this is the CH attached to O, these different chemical shifts. And then look at the actual area under the curve, or the integration, the value that you're given for the number of hydrogens. So this one tells you there's 3. This one tells you there's 9. So really, if you get a singlet with 9, it's going to be a carbon attached to 3 CH3s. This one is a CH2 because it tells you 2 on the spectrum, and this is also CH2 because it tells you 2, and you've seen from here that they are attached to, this one is a C double bond O and this one is O. So this is telling you effectively you've got a CH2 on either side of the ester group, isn't it? You know it's an ester, yeah? And then finally the splitting pattern. So at your 1.2 you've got a triplet which tells you it's a CH3 next to a CH2, yeah? Like I said, the singlet with 9 hydrogens must be this arrangement. 2.3, it's a quartet, so that must be a CH2 next to a CH3, and 4 is CH2 next to oxygen. So there you go. When you put it all together, you can see there are 4 environments that meet all the requirements, and that's it. What a marathon, hey? I think well done to all of you for finishing the exam and managing to, a lot of you managing to stay focused throughout it, because it is, it's not easy to do one of these exams and stay focused right to the end. Okay, see you soon. Bye.